8.2, proving triangle similarity by angle-angle similarity. Essential question, how do you prove triangles similar by angle-angle similarity? All right, angle-angle similarity is going to be a shortcut for the dilation transformation. We're going to be able to see with a few indicators whether a dilation has taken place. And our first one is our angle-angle similarity. So if you can show two pairs of one angle are congruent to two pairs of another in a triangle, then the triangles are similar. Okay, we're going to determine whether the triangles are similar. And if they are, we're going to write the similarity statement. Okay, so for the first triangle, I see that the measure of angle C is 26 degrees. And I see that the measure of angle D is equal to 90. Looking at the other triangle, I see that the measure of angle G is equal to 90 degrees. So already I have a pair, and I am going to try to figure out the measure of angle K, and I'm going to do that by subtracting from 180, and I get 26 degrees. So I see two pairs of angles. I see a pair of angles here, and I see another pair of angles here. So I know that, yes, they are similar by angle-angle similarity. Now it also asks me to write the similarity statement. And that's when we put the letters in order. It doesn't matter how you start, it's how you finish. CDE is similar to triangle. And remember, we want C to go with K, and we want the right angle D to go with G. And there's only one letter left in the triangle, and that's going to be H. And that's the similarity statement. We would like to prove these two triangles are similar, and we're going to do that with a two-column proof. I first write down the given, and I already have a pair of angles that are congruent. I'm looking for another pair of angles that are congruent, and that will be this angle here that they share in common. This little triangle and this big triangle share that in common. So I'll say angle A is congruent to angle A, and that'll be reflexive. So now I'm ready to say that the triangle ABE is similar to triangle ACD, and that reason will be angle-angle similarity. So in a lot of ways, this is a shorter proof than triangle congruence, because you only have to prove two things. Number one, we have some parallel lines. Parallel lines always give you information about angles. So I can say that angle S is congruent to angle U, angle S is congruent to angle U, and that's because if two lines are parallel, then alternate interior angles are congruent. Now I can show the other alternate interior angles, but what I think I'm going to do is remind you about these two angles. Angle 1 is congruent to angle 2, and that's because vertical angles are congruent. So I now have two pair of angles that are congruent. So I can say for triangle SVR is similar to triangle UVT, and the reason is angle-angle similarity. All right, let's do another proof. Now notice that I'm trying to prove sides are in proportion. So this is going a step beyond. I'm going to start off with the parallel lines, and the parallel lines are going to give me some angle information. And so I'm going to be given that this angle is congruent to this angle. So angle CBD, I must use three letters because there's more than one angle B, but there's only one angle A, so I can get away with that. If two lines are parallel, then alternate interior angles are congruent. I'm going to use the reflexive angle for both triangles, and that's going to be reflexive. Now I can establish the triangles are congruent. Triangle CBD is similar to triangle CAE. Be very careful making sure that the letters align, and that's angle-angle similarity. Now this is not what we're trying to prove. We're trying to prove that sides are in proportion. So now that the triangles are similar, I can now work with the sides. So BC, first two letters, is to CA, and then DC, first and last letter, to first and last letter with just CE. Now, when we were working with congruent triangles, it was CPCTC, but here we have to say corresponding sides of similar triangles are in proportion. Proportion is when two ratios are equal. So I had a ratio here and a ratio here, and I set them equal to each other. All right, here's another opportunity to show that triangles are similar and to write a similarity statement. I'll let you check that in the book. Let's move on to this problem. It's a problem in which we are faced with kind of a realistic problem. We have a pole. We have no idea how tall that is, but we do know its shadow is 50 feet. We have a girl who is 5 feet 4 inches, and her shadow is 40 inches. And we would like to figure out the height of the pole. And sometimes students find that if we make the triangle, they can see it a little better. And these are really right triangles. And the reason they're right triangles is these people are standing straight up to make a right angle. And the rays of the sun are coming in a parallel fashion. I should have written it the other way, like this. The sun rays are coming in a parallel fashion. So we have two angles of one congruent to two angles of the other, and that's these corresponding angles here that are congruent. So some students like to put the letters in. That makes them feel more comfortable. D, E, F. And so then they'll say triangle ABC is similar to triangle DEF. And then once they get this, they set up the proportion and substitute the numbers and get the answers. That's one way to do it. Another way is students see the triangles are similar and just start setting up the heights in the shadow. So the height of the woman to the shadow of the woman equals the height of the pole over the shadow of the pole. So this will come about with the proportions as well here. So the height of the woman in inches is going to be 64 inches. Her shadow is 40 inches. The height of the pole is unknown, so height of pole, and the shadow of the pole is 50 feet. Now I want you to notice the units. This ratio here is inches to inches, and the inches will cancel and we'll just have 64 over 40. The height of the pole has to be in feet, feet over feet, and then when the feet cancel, this number here, height of the pole, will have to be in feet. Now at this point we can now cross multiply, and when we cross multiply, that'll be 64 times 50 equals 40, and then we're going to height of the pole. And then we're going to divide both sides by 40. Height of the pole equals 64 times 50 divided by 40. Use our calculator, and height of the pole will be equal to 80. And remember that 80 represents feet. And so there's our answer, 80 feet. All right, let's take a look at this problem and see what you can do. Now that we know that the pole is 80 feet, they're asking us, what if a child is standing right next to the lady, but he's 58 inches tall? How long will his shadow be? And see if you can answer number 5. Okay, so stop the screencast and see what you can do. And here's the answer. Height of the child to shadow the child, height of the pole to shadow the pole. Remember the pole is 80 over 50, which reduces to 8 over 5. Do some cross multiply, and we're going to get 92.8. Remember, the height of the child is in inches because both of these, this ratio is in inches. Now, when you're outside and you want to figure out the height of a tree, which remember could be dangerous if the tree's really tall, so here's a way to indirectly find the height of the tree with information that you can use. And this is the end of the screencast.